Call is now being recorded.
Okay, so we will solve 9.5. Okay, and what it says that there is a triangle which is something like this. So we have a roller at the left end and then at the bottom as well, and then you have 3 meter. This is also 3 meter. Yeah, and there are forces perpendicular to that, which is 15 Newton per meter square. And given this is x, this is y. Yeah. So you have that, and what you are supposed to do is solve using. So consider one element triangle. So this is one element triangle. Boundary condition given. The is boundary condition is constant. So you can see that. Okay. The AC is subject to traction normal to the S. So assuming Young's modulus given E equal to 3 times 10 to power 11 Pascal, and the Poisson's ratio nu is given to be 0.3. So it says construct the weak form corresponding to generalized boundary conditions given in section 9.5. Construct the stiffness matrix, calculate the global force matrix, solve for unknown displacements, and so on. Yeah. Okay. So as far as the triangular element is concerned, we already know how it looks like. So you have 3 noded element like this. Yeah, and what is given to be is 3 meters here, 3 meters here. So you can find out k, and like also you can actually use xi 1 and xi 2 system as well. Yeah, so from this x y system you can change it to, so let's call this one as node number 1, this is node number 2, this node number 3. Yeah, so and so that you have node 1 here, node 2 here, node 3 here. Yeah, in transformed or the xi1 xi2 system as well, but instead of having 3 here, you have 1 here and 1 here. Right? So you can also have this way, so that you can straight away you can write. So we are looking at different way of solving the same problem. So what we get? We get 0 0 1 0 0 1 and so on. And based on that also you can, so the n1 xi1 xi2 is equal to xi1, n2 xi1 xi2 equal to xi2, n3 is equal to 1 minus xi1 minus xi2. Yeah, which is straightforward. How xi1 is nothing but x over 3, right? And xi2 equal to nothing but y over 3 simply. Yeah, so this is straightforward because you know that the our triangle, this one, which is the length is 3 here, 3 here, we are converting into 1 and 1. So keeping the same order, the same element number, you will see that you can scale it directly. You can write it like this one. Yeah, and accordingly you can find out the stiffness matrix. Right? Stiffness matrix, again, we know that finally the k is given by, remember, you are going to write as b t d b right? And then you have multiplied by area. Yeah, so this is what K is. Yeah, and accordingly we can write straight away. Yeah, so yeah, so we know what meaning of B, we know what is the D, so we know how to make it. So stiffness matrix, to follow the standard procedure, we'll do it. Main thing here is finding out what will be the U matrix and F matrix vectors. So that's what we will concentrate on. So we have, when roller is there, that really means the displacement, there is no displacement upward here, right? So that means if you have a triangle like this, so that means if we are calling 1 here, 2 here, 3 here, then you have u x3, right, u y3. Here you have u x1, u y1, u x2, u y2. Okay, now given this one, main thing here intention is to how to identify which value is what. So u as such will be equal to u x1, u x2, u x1, u y1. So okay, u y1, u x2, u y2, u x3, u y3 transpose of that. Yeah, okay, and that means this will be equal to what? So look here, we are saying that this is cannot go upward, so it can move because the roller is there. So roller is just a, how we denote basically the constant basically. So what it means that it cannot go up and down, but it can move this way. Yeah, so that really means this point can move this way, but this point cannot go up. That really means that our value, this value, this will be 0. Why? Because this point cannot go up, so this becomes 0. Similarly, this point can go up but cannot go in horizontal direction. Yeah, so that means this value is 0. Yeah, and now this point, you see that here you have constant that this cannot go this way, and here you have constant that this cannot go this way. That means this point neither can go up nor in horizontal direction. So we have both this and this is equal to 0. Yeah. So similarly, we have to write that here, and what will we write? We write this that we do not know, so we write ux1, uy1 is equal to 0, so we write 0. Then we have 0 again, so we write 0. Then we have uy2, so uy2. Then we have both 0, so we have 0, 0. So this is transpose of that. So this is how the displacement vector looks like. Okay, now we have to make a force vector. So what will be the forces? Everywhere where you have 0, there will be reaction corresponding to that. Yeah, so straight away we will write reaction here, right? And here we don't know. Here we have to see which all forces are which direction. Here, if you look at, there will be some forces. Let's write corresponding to these all. We can write those forces, and those forces will be the way we are denoting U. We can also denote F. So this will be F, x1, fy1, fx2, fy2, fx3, fy3 transpose of tail. Yeah. Now we have to find out what those values are, and what is given to us is on this triangle we have the forces going perpendicular to it like this, and the value is also given. So the value was 15 Newton per meter square. 15 Newton per meter square. Yeah, and we know that this is 3 and this is 3. So this becomes 2 is the length. Yeah. So of course, we know what is the meaning of that. We total force, total becomes 15 multiplied by 3 root 2 Newton, and half goes here and half there. So half here and half there. So that means 15 times 3, 45, 45 over root 2 here, 45 over root 2 there. Yeah. Okay. And this is, you see, this one is at as 45 degree, right? So that means component of that here, component of that. So finally, what do we get? So if we have in this direction, you have 45 over root 2, and this is 45 degree. So you get this cos, this multiplied by cos 45 degree, which is, so this becomes 45 over root 2 multiplied by cos 45 degree, which is equal to 1 over root 2. Yeah, so what do you get? You get 45 over 2. 45 over 2. Similarly, you get 45 over 2 here as well. Okay. So this and this point equivalent, the same value we have in the same direction we have. So finally, this is 0.1, this is 0.2. So what we get? F1, F equal to, simply we just write F is equal to, we get 45 over 2. Then you get here also 45 over 2, because in this direction 45 over 2, this direction as well. So 45 over 2. Here also the same thing. 45 over 2, 45 over 2. And here you get 0. 0 and 0. Not 0, but we will have a reaction because we have the reaction. So, okay, so we also have to write reaction basically. So let's call this because of the traction. So we write Ft like this one. Yeah. Okay. So final this Ft, because this is coming from the traction, and then we have the reaction forces. So wherever 0, we have reaction. So 0, here it will be reaction force, here also reaction force, and here also there is a reaction force. So finally F is equal to, then we have this direction, this reaction will be, so we get start from 45 over 2, then 45 over 2 plus R, let's write R Y1. Okay, then we have 45 over 2 R X2. Yeah, so this is will be R X2, right? And this R Y2, there will not be any reaction in upward direction because it was free to move. So 45 over 2, and then you have R X3 and R Y3, right? Transpose of. So this is what the force is. The rest is you have to solve. Right? Any question, guys? This you could have solved also using the N1 XY as area, right? A1 over total area. Yeah. So Ni is equal to Ai over. So you can also do this also. There are many ways of doing the same things. We can also do. Okay. Any question, guys? Okay. Okay, if there is no questions, then let's move on. So now problem number 9.6. Okay, and it says that an elastic body subjected to temperature tends to expand. This expansion is given in the form of the thermal strain, and it says this is equal to alpha T. Yeah, and then 1, 1, 0 T. Yeah. Okay. And where alpha is thermal expansion coefficient for isotopic material. Okay. And T is the temperature. Okay. The stress is sigma is given as stress is equal to D, and then you have epsilon minus epsilon naught. Okay, so this expression is given to you. So where the term corresponding to thermal stress is prescribed temperature data, develop a weak form and finite element matrices for the case of loads arising due to thermal expansion. Okay, so in this case, what changes? Here, these things remains the, so when you say epsilon naught, which is alpha times T and which is equal to 1, 1, 0, that really we are talking about what? Epsilon XX, epsilon XY, YY, and XY. Right? So this is what we are not we are talking about, right? So this is the like this one. Yeah. So this is given, which is a function of temperature. Temperature is given is constant. Some value is given basically. Yeah. And sigma is a relationship. What it is telling that we are sigma. In this case, just write like this one. So our sigma is in this case sigma XX, sigma YY, and sigma XY. Yeah, and earlier what we used like this. This equal to D times epsilon. So when we do our analysis, what you have to do is just replace this with this. That is all. Everything now remains the same. So only thing we have to change in your weak formulation is just instead of using this one, you are using this one, and then it's fine. I think in 1D also you have done that. Yeah, so it's not a big problem. Yeah, any question on this? Only the stress definition of stress has changed. All other things remains the same. Yeah. Okay. Okay. Okay, guys. So 9.7, it is asking the repeat question number 9.2 B2 triangular elements. So again, you can do programming to actually do it. Problem 9.8 also says develop a MATLAB program. Okay, so for that, so 9.8, it is telling you this kind of problem, right? So this is number 1, this is number 2, and you do some analysis with that. Yeah. Okay, so what it says, note, use the MATLAB. So do the MATLAB programming for this one. So I have sent you one of the programs, like in MATLAB, to solve such problems. Okay, so please check it. It's already there. I uploaded earlier. Okay. Okay, so I will skip this one. So please use you see the MATLAB program. Similarly, 9.9 is also for MATLAB programming only. And what it is in 9.8, it is telling you to use the 3 noded element, so something like 2 of them. And in 9.9, it is telling you to use 6 node quadratic triangular element. So instead of using this, you have to use this one. Yeah, so like this. And this also goes like this one. Yeah, so again, MATLAB programming only. So please do yourself. Okay, now 9.8. Okay, so again, this is also programming only. It's talking about, but still you see we'll look at the problem. It says problem is something like this. It is given dimension 0.4 meter, and from here to here this is 4 meter, and then it has the load here like this one. Yeah, and the loading is 100,000, sorry, Newton per meter. Okay, and then this is a cantilever beam. So what is given here, this is fixed at one end. Yeah, and load is downward. So these loads are downwards. Young's modulus is given. E is equal to 3 times 10 to power 11 Pascal. Nu is also given 0.3. And now you have to solve. Again, you can use the code. Basically, you can modify the code that I uploaded earlier. It says that meshing you have to do 2 by 5, 4 by 10, and 8 by 20. Yeah, so that really means 2 by 5, meaning that the whole domain you have to 2 rows and 5 columns. So you make something like this. So you have these elements, quadrilateral element, rectangular element actually, and then you solve it. 4 by 10 means you further refine it, and then you solve it. So this is all to be done using programming only. So please do all those. Yeah. So all of them, what you have now is mostly programming based only, actually. Yeah. So 9.11. So 9.11, and it says you have a problem like this, and then there is a hole here, and there is a force this way. Tensile forces from both the sides. This is X, this is Y. Yeah, and what it says that the dimension is given. So this is diameter, the radius of this. So finally, if you want quarter, if you are plotting, this looks like this, where the radius means from here to here is 2.5 centimeter. Okay, and the plate is 20 by 20 centimeters. So this is the plate, the whole plate is 20 by 20. So this becomes 10 and this also becomes 10. Yeah. Okay, and other things are given. E is given 2 times 10 to the power 11. Nu is also given 0.3. Uniform T is given 10 to the power minus 3 Newton per centimeter. All right. Okay, is given. So this is what these things are given. Okay, calculate the maximum stress component sigma xx. So you have to find out maximum sigma xx in the plate. Grade the mesh versus the hole. What it's telling you is to grade the mesh towards the hole. An example of such mesh is given in chapter 11. So it is talking about case the value applied load and the stress is sigma xx. So you have to use the programming again. Well, you can definitely do it. Now what is the motivation of doing this one is, as you know, when you are applying some load, if there is a plate like this one, and if you remember from your solid mechanics class, when you pull it like this one, what happens? You will have some stress here, and if you calculate the stress here, the stress will be higher. Yeah. So why? Because total load here, for that you have the whole length here, but for this one you have the lower length. Yeah. So because of that, there will be high concentration here, right? And on top of that, you have also, even at this point, even it will have much larger. Yes, it's more than the average basically. Yeah. So that the stresses are high, that really means that if you want accurate result, then you have to make meshing, design the meshing accordingly. Yeah. So in this case, we can analyze just quarter of it. And why quarter of it? Because this will give you the result. And this is symmetric about this, meaning that here you can same problem you can pose this way. Yeah, you can have, since this is symmetric about this, so such kind of tricks also you can do during analysis. So if you have this is symmetric, so you take 1/4, and you know that this one is symmetric line of symmetry, right? So that means there will not be any displacement here. Displacement in y direction will be 0 along this, and here, yeah. So, and also okay, so for first this one, so there will be no displacement in y direction in this case. So this will be equivalent of this. So you have a roller basically like this. Yeah. Okay. Now regarding this, since you have the load going this way and this way also, yeah. So same force both the sides. So you also see that this is line of symmetry. There is no displacement here as well in both the directions. So you can also have actually a roller here. Huh? Okay, and that way you don't have to analyze the whole thing. Yeah, it's that means you have the computational advantage here. You just analyze 1/4 of it and you are fine. Still, there is a problem because as you know, that stresses the forces, of course, the half force you have to keep here, and there will be high stress where there will be high stress here. Yeah, you know that. Hence, you have to have finer element this side and as you go here, it can be bigger. Yeah, so meshing is one of the things that you have to be careful. So accordingly, when you are going to create element, you will create a smaller element here. So let us say you will create some element here, something like this. So you will create a small element here, say maybe triangular, let us say like this. Yeah, and as you go further, then it can be a bigger element. Yeah, so you can have like this, for example, right? So it is so this is just an example. Yeah, so of course you have to experiment with it. When you say smaller, even smaller you can go, right? You can have something like this. Yeah, yeah. So more refined this here, the better result you get. Yeah, because the stresses here will be high, so you need to capture it. Yeah, so this is more like a trick, basically, the when you do analysis, how to like analyze the minimum structure. Any question, guys? Yeah. Okay. Okay, so your 9.12 is similar to 9.11, but it says the hole size is more. Yeah, so here it says the radius is equal to 19 centimeters. So, and but it's the same thing. Okay, so you can do it. So 9.13, it is about the axis symmetric problem, so rotational symmetry, and this is okay. So of course all the details are given there. You have to prove only. So prove the weak form is this and all. So but here, what is the meaning of the axisymmetric problem is, right? For actually some picture is also given. So axisymmetric is like this. You know that the cylindrical system, which can be something like this. Yeah, this is a disk, circular disk. Yeah, so this is R system, and you have the H system here. Sorry, this is Z. Yeah, and the height is H. Let us say this is H. So this is 2D plate. Yeah, this is 2D plate. Now what happens is it is possible that this is problem is axisymmetric, meaning that regardless of where you are, yeah, so you will have like two kinds of. So what I mean to say is, okay, on the next page. So the way you have, for example, in when you have a problem, it's a 2D problem, right? So in 2D problem, you will have some kind of stresses. All the three stresses, you have sigma xx, sigma yy, sigma xy. Yeah, so you have like that. Now axisymmetric problem will have everything axisymmetry, meaning that the forces, if force is one here, it will be everywhere, it will be symmetric like this one. Yeah, so all the forces will be applied like something like this. Yeah, so meaning that in that case, what happens is, in axisymmetric problem, you will get stresses which will be the forces will be applied on the circumference like this one, and hence you will see that there will be two kinds of extents only, and one will be the in the direction, in the radial direction, what you call it epsilon r, and then another will be in the circumferential direction, right? So this will be like, and there will no shear, yeah, no shear. To have a shear, you need some kind of asymmetry, yeah. So otherwise it's not possible, right? So since you have axisymmetric problem, means the forces are symmetric as well. Because of that, actually there is no shear, so there is no epsilon theta r, basically, yeah. So hence you end up with sigma, which will have sigma r and sigma theta only, and similarly epsilon will be equal to epsilon r and epsilon theta, and this therefore d will be also some different thing, yeah. I mean 2 by 2 only. So as given in your example problem, this problem, it is one new one. So anyway, so you look at this problem, how this looks like. This is for of course this universal system, so you have to look at the mathematics as well according to it. So do it yourself. If you have some any issue, just let me know, yeah. Okay, and then 9.14. Any question, guys? 9.14, and it says consider the 3-noded, the 6-noded element. Okay. So something like this. It says, so it's not. This is 1. Okay, it's not this way. Sorry, this. Here it is like this. Okay, and then there is a pressure which is given this way. Okay, so this is h/2 here, h/2, yeah. Okay, and this is P. This is the P pressure. This is have to show the element external force matrix F epsilon is equal to minus HP6, yeah, and then you have 104010 transpose of that. So this is what it is for external traction, basically. So for this force, for this pressure, it is asking the force vector will be like this. This is, yeah, and then you have to assemble the element force matrix to obtain the global external force F in the nodes 1 to 5 as shown in figure 9.23b. So this you have to show for this one, and then again same problem. You have different problem, and this is part A, and part B is telling that your problem becomes something like this, and you have the pressure given here, then length is L here, and another, this is also L, yeah, and then these are the nodes. So 1, 2, 3, 4, 5, and this is asking that for nodes 1 to 5, what will be the distribution of this force P, yeah. So this is totally on force, basically, and what how will you do it? So as far as 1 is concerned, like in case of this, you will this is 3-noded this is a three-noded element, right? So finally, this becomes three-noded element. So this will be like you have three-noded element, and then you have a pressure P given like this, and let us say this is 1, 2, 3, and you remember like you will construct a three-noded element, so such that N1 will be N1 will be 1 here, 0, 0, right? Then number 2 will be like this, yeah. So and then you have number 3, which will be 1 here, and then 0 here, so like this, yeah. So this is 1, this is 2, and this will be 3, yeah. And which component goes there? The component will be let's say called F I equal to P, right? And let's see from here to here, this is we are talking about the X, so it goes dx 0 to L. Of course, there will be Ni. So P times N I dx 0 to L, where N1, you remember, we can construct for N for 1D problem. Yeah, so it will be similar to that only. And so these forces will be like that. Yeah. And of course, all the pressures are perpendicular to this one. So only in X component will have that value, the other value, the Y component will be 0 in all the cases. Yeah, so any question, guys? Okay. Yeah, so do yourself, if you face any problem, just let me know, okay, during the class, or send me an email. And 9.15, it is about the 2D problem. So the problem 3D problem, sorry. So this is something like this. Yeah, so you try yourself. Again, this is the for 3D is not a part of syllabus actually, so we will not ask you any question from 3D element. Yeah, but this is for your own learning, so you can do it yourself. Yeah. Okay, so we are done with this chapter. One thing I want to remind actually is since we are talking about the the 6-noded element. So the 6-noded element will be something like this. Yeah. Right. Or in general, you write like this one. Right, like this one. Okay. So now, as we discussed earlier, if it is a straight line, these are all a straight line. Then when we define, let us say we call it, let's say 1, 2, 3, and then 4, 5, 6. Similarly, 1, 2, 3, 4, 5, 6. So when we are defining the coordinate, we have to carefully a bit. As we said earlier that if you have the quadratic edge, the quadratic sides. So if your sides are like that, if you have middle nodes like this one, and then you have 1, 2, 3, then 4, 5, 6, you can write like n, or you write x as a function of the x becomes equal to, sorry, so this you map to this system where you have 1, 2, 3, 4, 5, 6 system. Yeah. And in this case, you write this is I1, I2 system, and whereas this one is X1, sorry, X and Y system. Here you write X equal to summation of Ni Xi1, Xi2 multiplied by Xi. Right? And similarly, Y as a function of Xi1, Xi2 summation Nj Xi1, Xi2 multiplied by Yj. So in this case, summation is for the all the six. So I is equal to 1 to 6. I equal to 1 to 6. Yeah, so you can do it. Now, even if this is a straight line, you can still you can write it. There is no wrong in it. Only thing we are doing too much basically. So much is not needed. If it is a straight line, then we can have use some differently. As also this probably we mentioned earlier, that in that case, uh, if to begin with they are in the middle and also the straight line, then we can use the for a stiffness matrix the for n. What I mean to say is for defining x, we can just write x xi1 xi2 x xi1 xi2 is equal to we can simply have not in terms of xi1 xi2, I mean not in terms of n1 n2, we can have like a xi, what I meant to say is xi I, just a minute, x okay, so let me explain. So any comment? Okay. So what I mean to say is if you have 1, 2, 3, just only 3 points can define all the other points. Okay, so this point 1, 2, 3, you can map it as 3, 1, 2. This will be, so whatever the value of x1, x2, x1, y1, x2, y2 is, so here we will have in xi1 and xi2. Yeah, so that means if edges are straight, then in this case let's define n dash. Yeah, n dash 1 is equal to xi1, n dash 2 equal to xi2, n dash 3 equal to 1 minus xi1 xi minus xi2. Yeah, so here from this one we can write now x in general as a function of xi1 and xi2 is equal to summation of I equal to 1 to 3 now, and you have x n dash I times xi. So here summation will be for 3 only, but our n is different, our n dash. So we are using the original 3-noded one shape function to define x. Yeah, in contrast to a general formulation when you can use all the 6 nodes to formulate this. Yeah. So here this is also correct. You can also do this way. And you can, but this is for general purpose. For example, if it is a straight line, but your node is not exactly in the middle, then in that case, you can use this one. Yeah. Whereas this can be used when you have all the edges or sides which are a straight line and the middle node is exactly in the middle. So then you can just you can congregate this based on just three nodes only. As far as the relation between x and xi1 and xi2 is concerned, yeah, all others remains the same. Actual shape function you have to define the same way. Like actual shape function, you can write the way you write this also. So in all the 6 shape function here and here will be the same. However, the relation between x and xi will be different. So here it will be based on only 3 nodes, and here it will be based on all the 6 nodes. Yeah. So this is just for information basically. You can just go ahead with this also. You need to consider this way also, but just to add. Okay. Any question, guys? Okay, so main thing is solving yourself. More you solve this question yourself, more you'll be comfortable with all these problems. Okay. Okay. One more thing, guys. There is no class tomorrow because I will be on leave tomorrow. Okay, so I will see you guys on Friday. Yeah. And I think there is no need of any compulsory class because we are into last chapter. Only a few lectures are remaining, so we will do it. And anyway, our classes go beyond 15 minutes anyway, so yeah, so no need. So I will see you guys on Friday, okay, at 10 o'clock in the classroom. Okay. Okay, then see you guys. Thank you.